welcome to the Aerospace Advantage podcast. I'm your host, John Slick Baum. Here on the Aerospace Advantage, we speak with leaders in the DoD, industry, and other subject matter experts to explore the intersection of strategy, operational concepts, technology, and policy when it comes to air and space power. So if you like learning about aerospace power, you are in the right place. To our regular listeners, welcome back. And if it's your first time here, thank you so much for joining us. And as a reminder, if you like what you're hearing today, do us a favor and follow our show. Please give us a like and comment so that we can keep charting the vectors that matter to you most. Today, we're going to talk about satellite communications, or SATCOM for short. While it's not the flashiest subject, it's absolutely vital to how the United States intends to fight and win in the future. The ability to communicate, share data, and command and control forces distributed over large areas like the Indo-Pacific is fundamental to everything that the military does. Without it, military forces must act without coordination or positive collaboration. At best, this makes our forces less effective and at worst, can cause operations to grind to a halt, leaving our forces isolated and vulnerable. And the importance of this capability continues to grow. DoD is in the process of developing new warfighting concepts to maintain our competitive advantage against great power competitors China and Russia. All of these concepts share a common central theme, the importance of access to real-time information. We've got to be able to readily and seamlessly collect, process, and share information to achieve accurate situational awareness, improve the speed and quality of command decisions, and integrate operations to meet mission requirements. Tackling that information challenge is at the heart of another DoD concept known as Joint All-Domain Command and Control, what most call JADC2. And while most specific requirements needed to operationalize this concept remain murky, it's clear that satellite communications are going to play a central role. To help shed some more light on this topic, we have one of the authors of the Mitchell Institute's recent policy papers on SATCOM, Lukas Autenried. Lukas is a senior analyst at the Mitchell Institute Space Power Advantage Center of Excellence. Welcome, Lukas, and thanks for being here.
Hey, great to be back, Slick.
Lukas, to kick things off, why this paper now?
Yeah, thanks for the question, Slick. So at a macro level, we released this report at a time when DoD is thinking through how it intends to deter and defeat great power aggression. And for DoD's SATCOM enterprise in particular, this transition to planning for great power competition and conflict poses multiple challenges. But for the sake of brevity, I'll just mention three of them here. So first, we know that DoD's emerging all-domain warfighting concepts are creating new and more demanding requirements for its SATCOM enterprise to support. And second, DoD is working hard to define its SATCOM and other requirements for its joint all-domain command and control architecture that you mentioned. And so our report is intended to help inform some of those requirements. And then third, our warfighters are accustomed to operating in a world where our adversaries could not target our SATCOM capabilities. And this is certainly not the case anymore. Space is not a sanctuary, and in fact, our space systems are likely to be high-priority targets for any potential peer adversary. And so our SATCOM systems must be more resilient and agile if they are to provide the secure, on-demand connectivity required by our warfighters. But the good news is that there's some promising technologies such as laser communications and new SATCOM force designs that will help address these new requirements. The bottom line is that these technologies, combined with the consolidation of responsibility for the SATCOM enterprise in the U.S. Space Force, has really created an opportunity to build the systems our warfighters will need in the coming decades. And so that's what our report aims to tackle and why we felt it was a particularly timely topic.
Well, yeah, it seems very timely given where the Space Force is and its development of the future of SATCOM architecture. So broadly, what does this paper cover and what are some of the major takeaways from the study?
Yeah, so, as you alluded to earlier, defending America's national security interests depends on the ability of its warfighters to collect, process, and share information to make better decisions faster than its adversaries. And achieving this requires secure communications networks that can reliably facilitate the exchange of that information. And I think it's also important to note here that, the increased ranges and distributed manner in which U.S. forces will need to operate in places like the Indo-Pacific will inevitably make passing information through space necessary. So SATCOM really is the backbone, as we call it, that will tie together all of DoD's comms networks. But the challenge is that current SATCOM systems are too few in number, unresponsive to new missions, and lag both the evolving threat environment and cutting-edge technologies. So when we're talking about a space architecture, in this case the SATCOM architecture, we typically think about it in terms of three distinct segments. So you have the space segment, in other words, the spacecraft out on orbit, the link segment, or the comms links that connect the various nodes together, and then the terrestrial segment, so all the equipment within the terrestrial domains necessary to launch, operate, and exploit the spacecraft. And really, all three segments are in need of an overhaul, and our report sort of walks through some of the changes that are needed. So for the space segment, we argue that DoD should proliferate, disaggregate, diversify, and expand its SATCOM options by leveraging constellations of satellites in low Earth orbit and medium Earth orbit to augment its existing systems that today primarily reside in geosynchronous orbit, or GEO. And these proliferated satellites in multiple orbits would offer greater capacity and coverage, routing options with reduced latency, more optionality to meet mission-specific requirements. So basically, satellites in multiple different orbits offer complementary capabilities. And then also improved resilience against some forms of counter-space attacks. And then for the link segment, how you connect the satellites together as well as with terrestrial users, this is traditionally done using radio frequency communications, but these are increasingly becoming a bottleneck in terms of their performance, and they're also increasingly susceptible to adversary interference. So a better approach, particularly for space-to-space links, but also for space-to-ground, would be to leverage laser communications. Why? Well, you get an order of magnitude improvement in data rates to help manage the increasing amounts of information that needs to be transported. They're much more efficient in terms of size and power consumption, which is particularly important when you're talking about space-based capabilities. And they're also much more secure, so the transmissions are a lot harder to detect, and even if you can detect them, they're much more difficult to jam. And then you also need a terrestrial infrastructure capable of supporting this more complex infrastructure. So really, this is about handling that greater complexity and speed of these lower orbit, more proliferated constellations, as well as promoting greater interoperability and flexibility through the ground network. So think about how your phone can connect you to other users, even if they have a different model phone than you or use a different service provider than you. And that is all handled automatically without you having to change a bunch of settings or buying new hardware. With current DoD SATCOM systems, you can't do that. So really what you need are more flexible terminals that can seamlessly roam across different networks without dropouts and without needing operators to constantly, plugging and unplugging different cables or putting in a lengthy request for new hardware. And then the last thing I'll mention are the industrial-based considerations. So, the kinds of constellations we're talking about represent a paradigm shift in terms of how we produce satellites and their various subcomponents. But rather than building one or two bespoke satellites at a time, as we've sort of done in the past, we're talking about mass production on the order of hundreds of satellites per year. And this is really going to require a new approach to how the Space Force engages with industry to help realize these capabilities.
Now, as Lukas mentioned, the industry-DoD relationship is critical as the Space Force is working to field all of these new capabilities. And to better understand the dynamics of this relationship, we've got some incredible experts with us here today. First off, we've got someone who's known to many of you, Dr. Derek Tournear, the director of the Space Development Agency. And a little background here, SDA was established in March of 2019 to unify and integrate DoD's space development efforts, monitor the department's threat-driven future space architecture, and accelerate the fielding of new military space capabilities. So let me translate that. Deliver really complex space systems that we absolutely need and get this done as fast as possible. And given what's at stake, it has got to work. So welcome, Derek. It's an honor to have you here, and hats off to you for everything you do and you're working to achieve.
Well, thank you. It's a pleasure to be here.
Okay, so big picture, when you talk to members of Congress, the media, or the public, how do you explain why we should care about SATCOM? I mean, it can sound really obscure at first, but obviously it's the background of so much of what the military does.
Absolutely it is. I mean, if you look at what the military is expected to do now, right? So we are not just a homeland defense force. We are a force that has to project power across the world. And in order to do that, you have to be able to move rapid amounts of data from any sensor to any shooter and do that with low latency. That in the future, that's how wars will be fought and won. The ability to be able to control the information flow and be able to assign targets to weapons is really how we're going to fight wars in the future. And there's no way that you're going to be able to do that in any kind of resilient or time-sensitive manner without using satellites to be able to move those data.
Well, Derek, as you know, Mitchell recently published a paper on satellite communications, and during the rollout of the paper, we spoke with Dr. Voss of the Space Warfighting Analysis Center, or SWAC for short, and we also spoke with Stephen Forbes of DARPA. And as they described, SWAC does force design for the Space Force, and DARPA leads a lot of the S&T efforts for the underlying technologies. So where does SDA fit into this broader ecosystem of organizations working on the next generation SATCOM enterprise?
The Space Development Agency is set to actually proliferate and field and then operate these constellations. So if you look at everything, let's take this in perspective. So SWAC, what Dr. Voss is heading up, is really looking at what will be the force design, or what these satellites and infrastructure need to look like to be able to accomplish the mission. And then if you look at what DARPA does, DARPA develops the technology and does a demonstration to show that a concept is feasible. And that's where the Space Development Agency comes in. We're not trying to develop technology. What we're trying to do is we're trying to field a capability for the warfighter and do that in 2 years. So we take technology that's fairly mature. Most of that technology has been matured by folks like DARPA, and we get industry to build and deliver that as rapidly as possible. And we do that with input from folks at the Space War Analysis Center to essentially say what that future force design should be. And so that's how the whole architecture fits together and the different pieces and parts.
Awesome. So what's driving the need for the transport layer? And just to clear it up for our listeners, the transport layer is what we call the means of moving data, the satellites and their links. So from my vantage point, it seems like we've got a situation where not only do we face challenges because folks are demanding far more from the SATCOM enterprise, but the threats aimed at denying the use of our space enterprise are on the rise as well.
Absolutely, and it's even more so than the space threats. So from the Space Development Agency, we focus on the terrestrial warfighter and then work backwards from that to say what needs to be done in space. So let's take a moment to talk about how we have fought wars up till date, and then we can go into how the transport layer. So if you look at most of the networks that the Department of Defense uses, they're very limited in geographic regions. So if you look at a Link 16 network, that's a network that can be used to connect different sensors and shooters and different aircraft together. Those have limits of about 300 nautical miles. Why is that? Well, they were designed during the Cold War era, when essentially you wanted to tie all of your communications and your sensors and shooters together to be able to defend, against the Soviets coming across Europe, and that's kind of why that 300 nautical miles was set. In the future, we're going to be fighting wars that are geographically dispersed, and we're going to need to tie sensors and shooters together that are separated by much more than 300 nautical miles. And that's what the transport layer is all about. It is to tie existing tactical data links, like Link 16, together via space so that we can have our warfighters treat all of their systems as if they are globally connected, just like the internet does today. And the advantage of that is we will be able to use the existing radios and the existing systems that already exist in current aircraft, ships, and handheld Army units, and be able to tie those into this transport layer in space so that essentially, unknown to the user, they can move data as if they were connected directly to the internet and directly to a targeting cell that could be located in the United States or somewhere else in theater and move the data. And so that's the need for the transport layer.
Okay, so let's talk numbers. I've heard the transport layer described as ranging in a number from 300 to more than 500 satellites within the constellation, and that's quite a range. So what's driving those numbers? And I guess what I'm asking is, how much is enough, and how do your incremental tranches tie into this?
Certainly. So the way we decide on the size of our tranches, so our spirals, we look at the capability that is needed for a minimum viable product, and then we build from there. So for example, Tranche 1, which will be launched in September of 2024, that has 144 satellites. And of those satellites, the way we came up with that number was we looked at the Link 16 footprint that we could get from each individual satellite, and we said, for a given area of responsibility, we want to ensure that we have at least 90% coverage over that area so that we can start to effect a fight. And that 90% was a number that was agreed upon at our Warfighter Council, where we had representatives from each of the services and each of the combatant commands and the joint staff, and they said, yep, that sounds good. With that number, if we can get that, then we can start to effect a fight. And so that then, working backwards, that's where we came up with the 144 number for the initial Tranche 1, which is our initial warfighting tranche. Now for Tranche 2, we'll essentially double that, so that's where we'll get up to close to the 300 satellites, and that is so that we can assure that we get 2 satellites of coverage for that Link 16 for each of the users, and that just adds the resiliency. And so that's where that 300 number keeps coming out there. That's roughly 288, roughly 300, so we say 300. Now when we start to throw out numbers that are above 300, the idea there is we may want to have more than one network. So for example, we may want to have a UHF broadcast comm that goes down to a MUOS handheld radio in addition to Link 16. And so that would, rather than put multiple radios on a given satellite, it's actually cheaper, more efficient, and more resilient to just add more satellites with individual radios. And so that's why the numbers go from 300 to 500 depending on what missions we want to add. But honestly, the way we look at it is the proliferation, the more is always better. So we look at driving the price of these satellites down based on not only creating our own market, but essentially trailing off of what the commercial industry has done. Take those commoditized satellites and then get that low price and fly as many as we can for the budget that we have, and that's what allows us to continue to provide the capabilities with additional resilience.
Well, Derek, thanks for that. It's incredibly insightful, but I'd like to pivot to discuss some of the key technologies that are in use here. So SDA has been very active in conducting demonstrations on things like laser communications and on-orbit data processing, both of which I've heard you describe as critical enablers for proliferated space architectures. So why are these capabilities so important?
Certainly. So I'll start with the laser communication. So the more data that you want to shift around this network, you need higher and higher bandwidths to make sure that you don't overcome your network capabilities. And that's where laser communication comes in. So laser communication is a very efficient way to put a lot of bandwidth with a very little limited power, since you're limited in power on these satellites. So the ability to go from radio frequency up to laser for the communication allows you to get bandwidths that are on the order of gigabit per second for the same kind of power that it would take for an RF system to give you 100 kilobit type bits per second. So that's the main advantage. The second advantage is the laser communication, by nature of being a very narrow beam, allows you to effectively have low probability of interception and low probability of detection, so that you're jam resistant by design without having to build in any special waveform. And you can also go down to airborne systems in a means that have that low probability of intercept and detection, so that you can start to talk to platforms that are going into an area access denial environment, so that they can communicate without being detected in RF. So that's one of the major advantages of optical communication. Now the onboard processing, that comes in because we want to be able to move these data around the network, fuse the data together, calculate a fire control solution, do automatic target recognition, do all of that on board so that you can really capitalize on the low latency. Obviously, we're going to start off by just moving that data to different targeting cells on the ground, calculate a fire control solution, move it back up to the network, and then move it to a weapon. But ultimately, you want to do all of that on board, and that takes a lot of processing power to be able to do that. In addition to that, we want to pull in data from other systems that could be commercial or mission partners, and they could be operating at various different classification levels. So we need to be able to encrypt and decrypt the data just as quickly as we can move it with the laser communication. Now that's very difficult to do with a hardware solution without being very expensive and on a very large satellite. So we do that with a software solution, but that requires you to have a lot of onboard processing so that you can do, NSA approved software encryption and decryption on board in real time. And so those are the things that drive us towards these higher end onboard processing, which thankfully the commercial market wants as well. And so they've been commoditizing and driving down the price of those capabilities.
Well, Derek, it's my understanding that you're demonstrating optical communications as well, which is another way of referring to laser comm. So not just for space-to-space links, but also connecting the space layer directly with other forces in the atmosphere. So what's the significance of this capability, and how does it improve on the way that we do things today?
Absolutely. The key thing is to make sure that you can do it in a jam-resistant environment, and that you can do it in a means that cannot be detected by the adversary, or at least not easily detected. If you have a radio frequency beam that's providing satellite communication to an airborne system, that beam can be multiple kilometers wide, and so anyone that is in that beam will be able to hear that you're communicating with an aircraft. Well, that's a dead giveaway, obviously, that there's an aircraft operating in that AOR. With a laser communication system, that beam can be on the order of tens of meters. So you have to essentially be in that footprint to be able to detect that you're communicating with an airborne system. So that's one of the big advantages. The second big advantage is the aircraft itself, as it transmits up, in order to get the same amount of data from the air platform to the space platform to the transport layer. If it's a radio frequency based communication, it needs to use a lot of power to be able to push that data out there. A lot of power means two things. Number one, it's taxing on the platform, but number two, it's now broadcasting a lot of radio frequency that will spill over, that can be detected by monitors on the ground or monitors in space. So you can have a SIGINT satellite that will pick up that radio frequency communication from your airborne platform. Not good if you're trying to operate in a penetrating environment. So that's where the tactical laser communication really gives you an edge. Now, where there's a disadvantage is when there's weather, right? So these are optical communications. We're working with advances in optical communications to be able to penetrate clouds, and there's been some developments that you can even penetrate water. But to date, all of the optical communication that we're looking at is in the 1.5 micron, so it's in the infrared, which is blocked by weather and clouds and such. So you really can only communicate to users that are above the cloud layer.
Well, I've seen that SDA has begun awarding contracts to commercial companies to demonstrate interoperability of their own satellites with SDA's transport layers using optical communication terminals. And it's no secret that the DoD relies heavily on commercial space services, especially for SATCOM. So how are you thinking about leveraging commercial service providers, and what are some of the key challenges we need to address to better integrate those services?
Two ways. The first way is there are a lot of commercial providers out there that are building sensing constellations. And ideally, we would want to pull their data directly from their sensing constellations via a laser comm terminal to our transport layer so that we could fuse it with other data, fuse it with other commercial or government sensing systems, and then send it down directly to the warfighter. The challenge there is obviously we could be fusing data that's coming off of a commercial satellite that's unclassified, fusing it with classified data from a government system, and then putting that into a message that goes to an end user. So we need to have that multi-level security, which is a big deal, and that takes a lot of onboard processing, and that's a tech development. So that's a few years off. That's number one. The second one is there's a lot of commercial providers that are creating their own constellation of commercial satellites for communication. Starlink is one example, Kuiper is another example, OneWeb is a third. So there's a lot of those out there. And just like we use different commercial fiber providers for moving DoD internet data around, we want to be able to use those commercial providers to move DoD transport data around. So one of the ideas would be we would have our transport layer have translator satellites, if you will, satellites that could move data on and off a commercial network and on and off the DoD transport layer. And that would allow us to have an additional layer of resilience so that we could use the commercial network, whereas we could also then make sure that we can rely on the DoD layer for those tactical targeting needs when we can't rely on the commercial networks.
Well, Derek, it strikes me that a key initiative for your organization is to draw on a wider ecosystem of innovative space companies beyond just the traditional defense primes. However, a common concern we hear, and we've talked about it a lot on the Aerospace Advantage, is the barriers to entry that remain considerable for space technology companies. And from your perspective, what do you view as the greatest contribution of having an expanded roster of companies to draw from, and what can be done to encourage more companies to enter and stay in the national security space industry?
Certainly. Well, the big advantage is we just capitalize on more and more innovation. So as the commercial market grows for these space companies, They will start to come up with new technologies that can be commoditized primarily in those two areas of onboard processing and then the laser communication, because a lot of the commercial companies want to use laser communication as well. So we certainly don't want to shut any of those providers out, and we want to bring those solutions to bear. One of the key things that shuts these commercial providers out is realistically the draconian measures that are put in place for the financial systems. And the way we get around that, what we're trying to do within the Space Development Agency is award all these contracts firm fixed price. If we award contracts firm fixed price, that means that a lot of the reporting requirements that these companies are required to have in place, a lot of the accounting systems, they don't necessarily need to have those in place. And so that allows the lower barrier of entry, because they don't need to have an accounting system that is approved by the government that could be used for a cost plus fixed price contract, if you will, a cost plus contract where you can prove to the government that you spent so much money and they reimburse it. It's easier on firm fixed price. You tell the government you're going to deliver a product for a given price, government agrees to it, and when the product is delivered, they pay that price. And so that lowers that barrier to entry, and that's one of the things that we've really been advocating strongly for.
Well, Derek, I can't thank you enough for being here. Thank you for taking the time to come out and join us today on the show. We really appreciate everything that you and your team are doing at SDA.
Well, thank you. It's my pleasure. And stay tuned, because we're 37 weeks away from the launch of our Tranche 0 satellites, and it's going to be an exciting 2022.
That's a great segue to our next guest. With us now, we have Mr. Gregg Burgess. Gregg is the Vice President for Space Systems at General Atomics Electromagnetic Systems, one of the key players who is building these technologies. Gregg, thanks so much for your time.
Slick, thank you very much for having me on your show. I'm a big fan of yours and looking forward to our conversation today.
Well, Gregg, Dr. Tournear provided us a big picture view about why space communications are so important and what those future satellite constellations will look like. So if he's the guy who lays out the vision, it's your job to help him transform it into a technical reality. So can you help us understand the key challenges involved with building these next-gen SATCOM capabilities, especially when it comes to laser communications? And I've got to ask, what keeps you awake at night?
Yeah, absolutely. The General Atomics Division, GAEMS, that is focused on laser communications, is fully committed to the deployment of optical communications as the backbone of future national security space architectures. We've invested in significant production facilities with 7,500 square feet of optical integration capability in San Diego and over 700,000 square feet of manufacturing capability in Mississippi. We've got over 20 years of experience in developing multi-domain optical technologies, both at high power and at low power systems. And for these applications for proliferated laser communications, we have a low size, weight, and power optical communication terminal system that's technologically advanced, and it's designed both for production efficiencies and to meet all the most challenging requirements that the Space Development Agency has put for the system. The combination of a mission-focused manufactural design and large capacity development infrastructure means that we can meet the requirements and deliver hundreds of units every year on budget and on time. The new world order we're in the space business is really getting into constellation production. And while in the area of radio frequency electronics and digital electronics, there's a long history of space production and ramping up. In the optical area, this is new for us. Typically, optical payloads are carefully hand-built, hand-tweaked systems for space that frankly take months or years to put together. In the satellite communications world, we're now looking at production not in onesie-twosies, but ranging in the hundreds of laser communication terminals. And these are not simple radios. They're pretty complex devices with multiple moving mechanical assemblies, lasers, optics that have to be aligned. And so the key challenge here is transforming a industry that's typically going from a hand-built type of product to a high volume production. So it's that transition that we're investing in right now at General Atomics, and I think is one of the key challenges for enabling laser communications.
Okay, Greg, give us an idea on how near or far the potential is to field this capability, and how soon could they be operationally deployed in the field?
So we recently put up 2 laser communication terminals on an internally funded project. Unfortunately, there was an issue with the launch vehicle, and we've not been able to test those. So we are currently building a next generation set of laser communication terminals that we hope to be launching in the 2023 timeframe. So we will have 2 production units completed by the end of this year. That's how near term that is for General Atomics. As Dr. Tournear talked about, towards the end of 22, he will be seeing the first launches from the Tranche 0 systems. So this is near term. We're talking about in the next 6 to 12 months, we're going to be having systems in space demonstrating this capability in low Earth orbit.
Okay, so unlike in the past, designing and building this technology also involves mass production. And given what Dr. Tournear laid out, we are talking about hundreds of satellites being deployed in a relatively short time span. So that's a lot of extremely high-tech gear built on a tight schedule. What are some of the challenges you see from the production and integration advantage when you're looking at manifesting this vision?
Yeah. Well, right now, as in many industries, our top challenge is frankly in the supply chain. With all the impacts that have happened globally from COVID. So one of the things that General Atomics is doing is working on multiple sources for some of our key technologies. And we've been investing actually in inventorying key components from our suppliers for these systems. What the key challenge is for integration and test is, as I said before, going from hand-built systems into production for our optical capabilities. And so to that end, we're developing automated test systems for each of the components of the laser system as well as the receivers. Our objective is by the end of the year to get to a capability of producing one of these systems per day. In order to do that, we have a set of technologies that do automated measurements, alignment of the optical fixtures, and automated interferometric measurements, which provides a key measure of quality at the end of the system. The second part of this is, as you know, in the space business, these sensitive components have to go up on a launch vehicle, and they experience quite a significant amount of vibration. And while we design our systems to survive that environment, once they get on orbit, sometimes there's additional calibration that's required. So part of what General Atomics is doing for our laser communication systems is designing built-in calibration capability. So once we get on orbit, we can test out the systems to make sure that they work before we attempt our first communication link with each system. It also allows us to assure that we've got consistent quality between each of the laser comm systems once they're there, so that when we go up to connect either with our own systems or, consistent with Dr. Tournear's vision, connecting with other companies' laser communication systems, our expectation is that they'll work the first time because we've driven out all the variability in our on-orbit calibration capability.
So what about your team? I know satellites are all about technology, but it takes people to innovate and produce them. And this is happening when there's a surge in demand in the space world. So not only do we need smart and experienced folks, but they also need to have the right clearances given the sensitivity of these programs. So how do you approach that as a corporate leader, and what is your strategy to grow this talent and retain them?
So one of the advantages that General Atomics has is we have a fair amount of geographic diversity across the United States. In our space business, we've got our central operations here in the state of Colorado, but we're also deployed to San Diego, Tupelo, Mississippi, Huntsville, Alabama, and the Northern Virginia area. So that allows us to access talent in each of those areas. But as you know, it is a pretty competitive environment right now in the space business for talent. So we are using that to our advantage to hire into these different areas. And we're fortunate that in especially Colorado, Alabama, and Northern Virginia, there's a great deal of talent who have clearances. And so we're pulling into that talent pool. We aggressively clear people before we hire them in. and we frankly do our best to get people in on short order. The other part of this solution for cleared talent, however, is to make the subassembly components unclassified. And for the laser communications terminal itself, it is a commercial product, so we don't need to have cleared technicians doing the final integration and test of the system. And other parts of our satellites, we do have cryptographic gear, and that does have to be handled separately by cleared individuals. But a part of our strategy here is to keep the manufacturing team uncleared, and it's really the select design engineers that have clearances. And I think that's quite frankly a common practice throughout industry. So we have a robust training capability here at General Atomics. Because of the diversity of the technology that we have, we do have to cross-train people between folks that are expertise in high-power electronics and laser communications. So we have training curriculum across the board to bring our people into those fields on the engineering side. On the technician side, we've got very high pedigree programs for training folks in NASA-certified assembly and soldering techniques. We focus that at our facility in Tupelo, Mississippi, where we've invested heavily in the ability to do high production space electronics.
Gregg, you've been in the defense world for a long time. Can you talk to us about what we're seeing in the space community from an innovation and production standpoint? As I see it, this is, essentially the second space race, and we're at a moment where the fundamental paradigm is changing. What are some of the biggest factors that have evolved over the last decade, and where do you think we'll be when we hit 2030?
So the real revolution that's taken place in space over the last 10 years has been what I would call miniaturization. We've moved from satellites that are essentially the size of a large automobile doing RF communications or a small truck to things that are the size of a dorm room refrigerator. So the real revolution has been in getting to small satellites to do operational missions for the military. The first program that did that was a program I was involved with, which was the Geostationary Space Situational Awareness Program, or GSAP, for the Air Force. That's now one of the premier Space Force programs. And that was the first operational system in national security that was a small satellite. What Dr. Tournear is doing is leveraging the enormous investments that are going on in the proliferation of these small satellites, now numbered in the hundreds or thousands in low Earth orbit. So the story over the last 10 years has first been the miniaturization of nationally important capability from large satellites to these small satellites. And now the next revolution is really in proliferation in numbers. In the past, the focus on these systems has been in geosynchronous orbit, where a satellite hangs over a specific part of the planet and provides continuous communications to a single area. We're now replacing those large, very, very expensive satellites with proliferated systems in low Earth orbit that provide much, much higher capacity over a geographic area and provide interconnectedness between multiple types of constellations. Where this is going to benefit the national security of the United States is providing a much more resilient proliferated capability, so that the warfighter has the flexibility to use multiple systems and multiple satellites provided by multiple contractors. This is going to provide a critical strategic capability for the United States going into the future. And it's all been enabled by the miniaturization of technology in space and the ability to do manufacturing in space on a large scale. So looking forward into the future, for 2030, we're going to have multiple commercial constellations fully operational, providing 5G service globally. The next revolution may not be in space, but it may be into the terrestrial part of these systems, where individual receivers, either for optical systems or for radio frequency communication systems, will be able to operate between all of these different systems that are out there. A warfighter will be able to pick up a receiver and talk to any one of the commercial communication systems out there, as well as his military networks, to provide a fully resilient capability. The future in laser communications in space will be much more routine operations for interconnectedness between the different systems. Really, over the next year, we're going to be testing this out for the first time, interoperability between different companies' systems, and I think we're going to have natural hiccups in that process. It's going to have to be a fairly careful, planned out activity for each of these links to go between systems. Once we get to the 2030 timeframe, the interoperability will be a given. And all of the different systems will be operating on the same standards. And I see that Dr. Tournear's vision is going to be realized at that time.
So let's take this back to Dr. Tournear's vision for SATCOM. From an industry perspective, how do you see this evolving from a crawl, walk, run perspective? And how will we know when we're hitting these junctures, and what will success look like?
So the crawl and the walk phase is over the next couple of years as Tranche 0 and Tranche 1 get deployed. We will be finding out how the vision of interoperability really is going to work once we get these systems on orbit and we begin to connect the systems between different vendors' approaches. I believe that there will be some significant challenges in that. Interoperability has often been an issue for the Department of Defense when they deploy new systems of different types. I think we'll have reached success when we put up a new constellation and it seamlessly interconnects into the existing systems without a long cycle of initial test and checkout. So when we put up a new constellation and within a matter of weeks, it's up and operational with its sister systems, I think we will have reached success. And for the warfighter, when they will have a choice between multiple communication systems, providing different paths between the warfighters, and that operates seamlessly from their terrestrial or airborne terminals, where it switches between systems based on availability, that's when we will have achieved, I think, true success. This investment in what's called the transport layer or the foundational communication layer is a very key investment because we don't really enjoy that today for our warfighters. General Atomics is committed to providing full global 24/7 situational awareness for our warfighters. And in order to get that data down, it's going to be essential that we get these communication networks up and operating.
All right, any parting shots?
Well, General Atomics is really excited to be at the forefront of this new vision for national security space. As we know, our peer competitors in this space are not resting on their laurels, and it's absolutely critical that we get to these kind of proliferated architectures that Derek Tournear is pushing forth, and we're excited to be a part of it.
Okay, well, again, thanks so much for your time today. Really appreciate getting your inputs.
Thanks, Slick, and I really appreciate that you have chosen to focus on this topic. It's absolutely critical to the nation's future, and we want to make sure that everybody is on board with where SDA is going.
Thank you, our listeners, for your continued support, and thank you for tuning in today. We've got a lot of new and exciting content coming your way, and this year, we're headed out to Aerospace events near you, so don't forget to follow or subscribe to the podcast. Follow us on Twitter, Instagram, Facebook, or LinkedIn to find out where we'll be and what the Mitchell team has in our site picture. And please, don't forget to leave us a rating. Hit the like button and follow or subscribe to the Aerospace Advantage. Also, leave us a comment to let us know what you think about our podcast and let us know areas you think we should explore further. Please visit us at mitchellaerospacepower.org to read the latest reports, events, and analysis that are charting the vectors for our air and space forces. Thanks again for joining us, and we'll see you next time. Stay safe and check 6.